Okay.
Yeah, we can now start.
Is there a microphone or?
Microphone? No, actually, this will catch it.
This will catch it.
Yeah, yeah.
Should do, no?
Yeah, that's it.
But you should come front. I can't speak too loud today. So. I have a cough, so.
Okay, let's get started. Sorry for the delay. Welcome everybody to the second part of Raghu Meka's talk. Raghu will continue his discussion on the 3AP's bounds of 3APs.
So today I want to go more into depth about the result that I mentioned in previous talk on Wednesday. So just to recall, the question that we were interested in was, we have a set A subset. When can we guarantee exists if I usually want three elements such that distinct elements are A plus B cases. Okay, and the result that I mentioned on Wednesday, and which I'll talk about more today, is that delta is into the minus 4. So as long as you have at least this fraction of elements, you will find three elements which form three distinct elements. Okay. And this was over the integers. And in the talk that day I mentioned, I discussed everything on finite fields, and that's what I'm going to do today too. But I want to pretty much give the entire picture for finite. Okay. So let me also say, I guess it's actually weaker than what's found, so let me not call it a theorem, but it's a result that we are going to talk about today. So let's say now A is subset of F3 to the and A is subset of F size of A is delta of CN. When the point that is not important, you can just think of it as some omega 1, really.
So capital N is 3 power.
Yeah, capital N is 3 power. Yeah. Then there exists distinct A, B, C such that A plus B exists. And this is all arithmetic over mod 3, or basically think of it as you're working over the finite field. Okay, so that's what I want to talk about.
So you're going to prove this for finite fields. Eventually, does it eventually lift to the integers?
Yeah.
Does it lift to arbitrary abelian groups also? Or?
The one that we had in our paper did not, because actually in our paper, what we do is we do induction on generalized arithmetic progressions. So one way, like in one notion of subspaces that you can work is you find a sub-interval onto which you have density increment over integers. You can't quite do that. You find kind of a multi-dimensional interval which you have some density increment and so on. So it got a bit hairy for us. But the argument of Bloom and Sisask actually work for all finite abelian groups. Much shorter, like lift is much cleaner there. It kind of has the same ingredients. The constant, for instance, is exactly the same.
Okay.
But it kind of gives a much nicer way. In fact, when we just about a month ago, Bloom and Sisask wrote to us that one of the calculations had wrong constants, which they updated our paper. Initially, it was points, these were 1 over 11, everything changed a little bit. Okay.
So how does it work? You do it for finite fields and then there's a lifting process. So use the same proof, you then do it.
Yeah, basically, it's not a black box thing. You have to do everything from scratch.
So this Fourier analysis that goes on.
Yeah, you have to do almost everything from scratch again. Some things are reusable, but many things aren't. But actually, the reason we were interested in this question to begin with because of some things for finite fields. And over finite fields, even if this result isn't interesting, we do get some new corollaries, which people did not know before. Okay, in fact, it's a very nice structural result, which I'm going to state now. And it might be useful for other things. And this, we were interested in results like this to begin with because of its connection to some parallel repetition things. But let me just state what is known. So structural result about finite fields, nothing to do with 3FPs for the time being, but it's an interesting standalone statement. And this has to do with how, let's say I have A, which is subset of, right? And there are results which essentially say that if A is big, okay, but A plus A hasn't grown too much, then A should be very close to the subspace. Okay, so those are the kinds of results that you're interested in. Or you want to say that if A plus A doesn't grow too much, A contains a very big subspace. Okay? So these are the sort of polynomial things like this are connected to polynomial Riemann-Roger results and so on. And as a part of these things, something that Sanders showed is that I have this. Okay, now the set is so big that by definition, A plus A is not growing much. Right? Typically, if I think of a small set, A plus A should be of size square of A. That is A. Oh, sorry. Yeah. Okay, so the set is already so big that it's not growing. Okay, so this means that you want to say somehow that there is some subspace inside it and so on. And what Sanders actually showed is maybe that's not quite exactly what you get, but something close to it is true. So there exists, basically for every delta, there exists a substrate V such that V intersect A plus A is very big. So the subspace is almost completely contained in A plus A. Okay. I'll write this down. And the most important thing here is the noise. Yeah, exactly. So what is the dependence on, there are two measures here. So one is how well is, how much of V is actually contained. Even if it's like a constant fraction of it is completely contained, that's still interesting. Right? But it also depends on how big V is. And what Sanders showed was that there exists subspace V with co-dimension O of our constant. I think it's epsilon. Okay. So the dependency for dimension is polygon. Okay, but this is connected to what's called fuzzy polynomial Riemann-Roger, and if you follow Riemann-Roger connect this polynomial, but it's basically saying any big set, maybe it itself doesn't contain a subspace, but once I have two copies, it contains a subspace.
So because you say we can increase it by in terms of the growth of A plus A, if you look at the size of A plus A divided by the size of A square,
Yeah.
that would be the normalized growth, right?
Right. But here, because
But not here, but I think
in general, yeah, that's the intuition. Like, basically there are versions where you compare the size of A plus A to adding like, maybe 4 times, and then you do all of these things. This is kind of the simplest version. Okay.
but there is one such version.
There are other versions.
One version that that if some 8 result 4 times, because it was 8, and that contains a.
Right. This implies that.
Oh, this is.
Yeah, exactly. This implies that. Yeah. So I'll tell you why this thing, but basically what we can do now is
But the dependence on the 4-dimensional, the delta really polynomial.
it's log 1 over delta to the 4. I think if you show O of log 1 over delta, that's kind of almost like polynomial theorem. Like, basically, if you have O of log, then the size of the set is like delta to some power. Like, the size of the subset. So that's why then that's like polynomial, whereas this is called the polynomial. Okay. And if you remove the 4, you'll say like, almost this will come down to like 1/5 or 1/4. Okay, so what do we show? What's the structural result that we show? Let me start rewriting everything. So all of the things stay the same, but this improves, or it kind of becomes incomparable. It becomes log 1 over delta to the power of 5. Sorry. But what improves is the dependence on that side. There was polynomial dependence on how close you were to the subspace. Okay, now you have like a very, very good dependence. So now you can start playing tricks like if you want the entire subspace to be in, I just need to take epsilon to the which you can afford. Okay. So this is a new thing that we get. For instance, in the corollary, it was known for 4 times the corollary, you get that there exists a subset of A, in fact, such that so there is a big subset such that once I add 3 terms, it's the entire subset is actually equal to a subspace. Okay, so here like we intersect with B, but now this is the entire thing is just a subspace. How do you get this? Basically, take epsilon to be sufficiently small and you work with parameters. These are some interesting corollaries or finite fields that you get out of Bloom methods.
So this is separate proof of the Sanders-like result, where you go into Sanders and
We kind of, use some of the ingredients that Sanders uses. So we can't say it's completely separate proof. Right? We kind of do the pre-processing more nicer, and then we have to still use his some of it. Okay, so that's the standalone method. But let me now go back to the 380 thing and talk about this. I'm not being very efficient, but hopefully I will learn soon. Okay, so in the proof, so the proof has 3 steps, right? Roughly, there is a structure versus randomness thing and so on. But let me summarize it in a more sort of analytic way as follows. First, let me introduce some notation. This is the density of A. This is the function which basically is supported on the elements of A. Okay, but it's not a probability distribution function, it's a density function, meaning so this is so that when I take expectation of mu A or a random element, you get exactly one. Okay, so we work with densities instead of probability distributions. Because probability distributions, usually you say you add up the elements, you get one. Density means you take the expectation of the function, you get. And this is much better normalization because when you move to subspaces and so on, you don't have to renormalize things. Like everything, the constant function, one is uniform density and so on, everything works across units.
Expectations are all taking over what?
Expectations are all over a random element in this ambient space.
In the ambient.
Exactly.
Small.
Okay, so whenever a function satisfies this and is non-negative, we'll call it the density. Okay, so density just means that it's non-negative and expectation x p of x. Okay, kind of a, you raise, if you put summation x equals 1, then it's a probability distribution function. You still think of it as describing a distribution. Okay, but this normalization is much nicer for us. So uniform density, uniform distribution corresponds to the constant function 1. Okay. So uniform distribution is constant 1 function.
It is size by one should be one.
Yeah.
Maybe one outside.
Oh,
Yeah.
yeah.
Actually, if you want to increase it to one, then it should be size of the set divided by size.
Size of
That's why the uniform distribution of density.
no, but when I take expectation of x, the chance that you land in I see what you mean. Yeah.
No, I mean the inverse 3 per n over 8.
3 per n over size. Yeah, fair enough.
Right. Yes. So okay, so when size of A is relatively big, this is still somewhat bounded. Okay, so that kind of measures how big the set size is. This 1 over del, this is about 1 over delta on the non-zero values. It'll come into picture here. Okay. Thanks for catching that. Okay, but we'll always work with densities because everything is nicer, especially when we go to subspaces and so on. Okay. And okay, so now maybe let me check. Okay, so the whole thing, or there was a structure versus randomness part, and the starting point is to say there are no 3 APs. Somehow there are not many 3 APs. Then that means you're not close to uniform in whatever sense. Then you have to get some structure, but the whole of the thing is built on a series of stuff. And this was the structure versus randomness lemma from the top. They said, if you don't have many 3 APs, then the difference conservation of A with itself is not lower concentrated. Okay.
Formally define what?
Again, I'll formally define it again. But this is, kind of, going over what we did on Wednesday at a high level, and then we'll dig into that. Okay, and then there's the next step, which is the spectral positivity part, which then this implies that takes high values as well. Okay, the switch from being not load concentrated to taking high values. Okay. And then there is the sifting part, which allows us to find density increment onto a sum set. Okay. I'm just recapping the outline from Wednesday, and we'll talk about some of the steps at least in more detail. Right? And then there is step 3, which was this almost period. Let's say once I find density increment on the sum set, you actually get density increment onto a subspace. Okay, so there are this sort of 4 steps.
Actually, the first thing, looking at the sum convolution is
Right. The normal convolution is not very constant. I'll tell you why this happens and everything. I think I can go over pseudo 1 and 3 relatively easily. In time 2 takes a bit more work. Okay, so I'll do that, and then in this time I'll do 2. Because in some sense 2 may be the most interesting piece, but I think 8 more. Okay, I'll do that. Most interesting piece from this one. Like the other stuff are obviously very interesting too, but like this involves the standard is very heavy. And this is a spectral positivity, and this is like some standard.
So this chain of steps, is this also a previous one or is it different?
One thing that's not there usually is this speed. Okay. And almost always you do density increment, but how you do the density increment is different. We're using the sifting, which again is kind of weird, but there are other things like Gauss uses it in his proof of similarity theorem. The dependent choice thing that we do is kind of there in some of his things as well. It's not like, this is only first time seeing it, it's there in other words. But this chain, this flip, everything kind of is but nice. Okay.
So in for example, Roth's original proof, the structured part is one where there is one Fourier coefficient that is large.
Right.
So if you assume that you get all of this.
Yeah, actually, that's a good. Like the chain is much easier there. So in Roth's original proof, the chain.
Why do you jump the density?
Yeah, but I was wondering if it is that you still get it, but
You lose too much in the parameters. So basically, in Roth's original proof, you say there are no PAPs, then there is a large Fourier coefficient. Large Fourier coefficient means that basically it's an equation on which you are biased. Right? Means you have density increment on a subspace of codimension 1. So you have very, very big subspace onto which you have density increment, but the increment is tiny, delta plus delta squared. You go from density delta to delta plus delta squared. Okay, and now you have to, let's say I'm shooting a constant factor, then I have to do this 1 over delta times. So that's where the codimension becomes 1 over delta. So in fact, you cannot do it I cannot find the subspace one direction at a time, which is what Roth is doing. You have to somehow find everything together. Or at least, find them in bulk.
So, but is it true that if your UA has the property that there is one Fourier coefficient that is large, will it automatically be not lower concentrated?
I think so. I think so. Yeah, it's a stronger condition. It's a stronger condition.
So you might want more concentrated.
Yeah, I'll define it. So not more concentrated just means that I'll define it like this. Okay, so let me go back to this normalization here. And some things to keep in mind. I'll talk about, I'll use some norms. All norms will also be expectation norms. Meaning if I have a function from f3 to the end, to R, the kth norm is and the expectation is over uniformly random.
Absolutely.
Yeah, typically K is even, so yeah. Okay. All right. And okay. So
How crucial is three here?
not a problem. Everything can be executed. Then there'll be some dependence on Q, which basically comes up in this like the deficiency and so on. So it's really doesn't matter much.
Three of the field.
Yeah. Three of the field. Yeah. Step 3 is definitely. Okay. So let me talk about step 0. Okay, which is what happens if there are no TAs. Okay. So in the talk I talked about the lower concentration because I think that's much more intuitive and that's somehow how we thought of it all the time. But in the proof, we can just work with analytic things and everything is fine. So let me do the analytic stuff and then I'll connect to the lower concentrated thing from the talk in a little bit. So what does no TAs mean, right? So if there are no TAs, what it really means that A plus A does not intersect 2A at all. Okay, there's no common, or like there are very few elements there. So think of A plus A as all
A plus B, A.
so
A plus B.
A, B are distinct. Okay. I mean, again, don't worry about the technicality of the same thing. Everything will be big enough that the picking the same thing will be used for the other stuff. Okay. Another way to think about it is basically if I take A convolved with itself, then its inner product with the function through A is close to 0. Really think of it just as 0. It's not exactly 0 just because sometimes you might put the same element and then it lands in here, but that's yeah, we'll do the switch.
That's the plus and minus.
Yeah. So this is the usual convolution. Okay.
Which is minus.
Which is the usual convolution is
Distribution of A plus B.
Of Z is X is expectation over Z of F of D and G of X minus. But you're taking two things and adding their sum should be okay. So this is, if you think of it as a function, it gives me the density of the distribution, which is taking two independent properties and adding. Okay. So this is basically close to 0, right? And which is equivalent to saying that so if I take the constant 1 function, its inner product with mu to A is 1. This is close to 0, so this is 1. So it's actually very close to 1. So let me just say it's bigger than a half. Okay. So intuitively, what this is saying is the convolution of A with itself is not close to the constant 1. It's some measure of distance from the uniform distribution. If it's uniform, then obviously it would be everything. But this is only in this inner product. Okay. And what we know about 2A is that it's coming from some A has high density, right? And high density essentially means that this function, the largest value is bounded. Okay. So you can use Holder's inequality.
Less than my negative something. Less than my negative.
Let me do abstract. Yeah. Okay. So this implies you can use appropriate high enough Holder's inequality, basically, to say that the kth norm is like half, or maybe 1/3. Where k is roughly of log 1/3. Okay, you have to use the right Holder's inequality, which I don't want to get into. Okay, basically, if you use Holder's inequality, you get some kth log here, and the whatever, like 1/2 plus 1/2, the other one here. But this is a bounded function in the sense that its highest value is basically like 1/delta. Okay, and if I use my q to high enough, then 1/delta will become raised to the power, so it will become a constant. So what thing does it become a constant? Around log 1. This is a trick between like infinity norm versus taking a high enough kth norm. Right? Over space, if I tell you the infinity norm is bounded by something, that's almost like saying you have done, the logNth norm is bounded. Okay? But this is some Holder's equality, right? And this is saying that you are bounded away from the constant one function, but the deviation is only evident when you take a very high norm. Okay? Remember that the norms are always sort of increasing as k goes. Because if this was 2 norm, then this would be very, very strong. And in fact, all of the old arguments would work. But the point is that you only get that this is high at a very big k. Okay? And this is essentially what lower concentration corresponds to. Like lower, if you take the kth norm, then it tells you about sets of density roughly 2 to the minus k and nothing smaller. Okay, again, this is notion between mean entropy and 2 to the k, which I don't want to go into. But just take it for granted. The intuition is that this is essentially equivalent to saying there exists many points. There are reasonable number of points where this gap is omega 1. Okay, this is one implication. That is the conceptual implication which is important. Okay, but analytically this is what it is. All right. Let's work with the analytic thing.
So omega 1. So if you think of this as you're saying,
This omega is like 1/3.
there's
Because
not necessarily large number of points, but this function and the function.
exactly. Yeah. Basically, you'd say, okay, what is it? Let's take this fraction p, and then you get p to the 1/k, and you immediately get p is at 2 to the minus k.
For diagnostics, we expect this to be 0.
Yeah, very small, exactly. Yeah, that's why random is very bad for this convolution. Okay. All right. So now, so we have this is the starting. Let me just use epsilon instead of 1/3 because the constants will keep getting changed and worse. So let me just use epsilon as a constant that keeps improving. Okay. Now there's this decoupling inequality that we show. Inequality says that if I have any two functions, in fact, this can be over any space. Someone's measuring the distance of the convolution from the constant one function. The worst thing is to take the difference convolution. But here you use it with the same F and like F and G both being UOD, but it's actually true more general for different. They're saying the distance of F star G from constant one function in K naught is always bounded by. Okay, again, this is some like standard Cauchy-Schwarz. You just have to do Fourier expansion and prove it.
Because the clear density, F and G are more dense.
F and G are more dense. Actually, otherwise it has to be the normalization of F and G are dense.
So the expectation is one.
The expectation is one. Things like that. We don't need non-negativity here. I remember that. I don't think you need non-negativity, but let me say you need that. So that's the decoupling inequality. It follows from expanding it out, as I said, and then using Cauchy-Schwarz and the Fourier coefficients. So, so basically what happens, you do everything in the Fourier space. The kth norm, you can again evaluate it by the Fourier expansion, raise it to the kth power. You just have to do like 4 lines of calculation. Okay, but I think as a standard inequality, it's good to know. It could be used for somehow the intuitive thing I think about is, if I have F and G, I'm trying to compare what does the convolution do. Well, difference convolution is the worst thing when you're getting close to it. Okay. All right. So because of this, knowing that the star convolution is big implies that the difference convolution also is big. So the corollary is, and this only works for measuring distance and constant one function. If I replace this with something else, it doesn't work. K has to be even. Like for instance, I don't know or don't think it's true at case one, like statistical distance that I think.
So just if we expand the thing out, we have Cauchy-Schwarz on the
Cauchy-Schwarz on the Fourier coefficient and
how to increase it to the power K.
K has to be. Okay. So now, this implies that so no 3 APs implies for some constant percent. Okay. So this is step 0. Right? Makes sense? So let's start with this, and now let me talk about step 1, how this flip happens.
It's not necessarily flip, no, it's just that that there is that this step tells you there are a lot of things bounded away from one.
But
you want to know that not just all of them don't come from below,
Exactly.
some of them will come from that.
Right. Intuitively, like if you look at this argument and follow it more closely, it only tells you that lot of things are below.
Okay.
I mean, the reason we are able to show this is big is because we know that there are a lot of things which are below. So far at least.
Okay.
But then we have to say why the thing changes. Right.
So the reason you get only at the lower band and not around, say, around 1. Not a concentration statement around 1, but about what happens to very low values. Is it largely because this K is this large?
No, you can even take close to 1. Maybe I didn't
I
understand.
see why a statement of this form implies that it is not lower concentration.
Oh, that's because of this. Like, basically,
Oh, I see.
right? So the smaller the K, the stronger your lower concentration violation is. We're saying, I have a lot more points where it's omega 1. This omega 1 is actually in the talk, I talked about like 0.1, but it can be half even to begin with. But then it degrades, like here it's 1/2, here it's 1/3. So it's like 0.66 or something.
Why is that a statement about lower concentration? All that seems to be saying is that
The absolute value is big.
Yes, so but it could be,
It could be, but really, if you look at it, so it could be that it could only be lower 2, it could be only upper. If it's upper, we are winning already. Right.
so this step, so.
Tells you that there has to be upper as well. There definitely has to be upper. Okay. So what is step 1? Again, it's something generic. So let's say Q I'm going to assume non-negativity for now. I don't think you need it all the time. It's a density and is spectrally positive.
Sorry. So this statement is not something specific about the thing inside being whatever, mu a star, mu a minus 1.
This statement. No, it's not. It's just a property of the norm.
If you have some function,
Yeah.
such that its kth norm is large.
Exactly. If it's F, then you get this. Yeah. But intuitively, for me at least, always things helps to think of it in terms of the sets.
No, in the sense that if I replace the star with the circle.
Yeah. It will still be true. Yeah, exactly. Yeah. It will still be true. So let's say Q is any density, but it's spectrally positive. Okay, what does spectrally positive mean? Spectrally positive means that all of its Fourier coefficients are non-negative. They're real numbers and they're non-negative. Right? Fourier coefficients over f3 to the n, they can be complex numbers. But here we're saying that they're real numbers and non-negative.
This is why you're going to use the negative thing, because something is going to be spectrally positive. Whereas
Right. Okay. So first, the claim is that is spectrally positive. Why? Basically, for coefficients, the different convolution are basically convolution. The standard convolution gives you the product of the Fourier coefficients, and this one gives you the product of the conjugate. Okay. So now what's the claim for spectrally positive thing? Basically, it's the following. If Q is a SP density. Again, I'm going to fudge the quantitative things a little bit because I don't want to sort of go into the weeds too much. Okay. And I tell you that it's deviating from the one function. Okay. In the case, no. It could be the upper, it could be lower. Right? Then you must have the K prime norm. That means the K norm deviation from 1, Q minus 1 K norm is 3. Okay. Then, in fact, the K prime norm, the K prime is like your epsilon, is actually away from. It's like a reverse triangle in the polynomial, which is typically not quotient. Like it should not for general densities. If this doesn't mean that the norm of Q will at least manifest itself. But if it's spectrally positive, it's kind of true, but you have to do something in K. So that's why I said, we're going to change the constants all over the place. This constant is not too bad, but. And here's where the concept is which happened, because again, you can think of it, the norm K prime not being big implies that there are many points, at least 2 to the minus K prime points, where you're taking the value at least 1.0.
So does it, so there you put omega of 1. So fact that it will be omega of 1 plus omega epsilon, and that goes smaller than
Epsilon is you start out with 1/3. Like here this 1/3 is like maybe from 1/6 here, just because of the way this 2 to the minus k thing works.
So that's a quantity larger than 1. But you're going to reapply the same fact for the k prime norm on Q now to show that there are a large number of points on which Q is larger.
We can always work with the norms from now on.
Okay.
Yeah, I mean, we do kind of do it in step 2. We do look at the set of, say that the set of points when it's big is big.
Good.
We do need to use that conclusion.
Okay.
Okay, again, it changes the epsilon a little.
No, exactly this one. From this, are you then going to conclude that there is a 2 minus k prime fraction of points where Q is
Bigger than 1, yeah.
bigger than 1.
Yeah, we are going to conclude that and actually use it in step 2.
That's almost average.
That's the average.
That's
That's the same thing there. Yeah.
Same.
Yeah. Okay, but this thing seems kind of miraculous, but actually, the reason it's true is something little bit like more real analysis 1/1. Okay, in the following sense, this is not a property of spectral positive density, but it's actually true about something about univariate triangle. Okay? So the true lemma that we show and use is the following. So let x is a real valued variable, and let's say expectation of x is 1. Okay. And A, B is that all of its odd centered moments are non-linear. So for even things, obviously this is non-negative, but the odd centered moments are also negative. Like for instance, it's saying x minus 1 to the power of 2 is non-negative, which is not necessarily true for many radicals. When you take the odd centered moment, it could be negative, it could be positive. Let's assume it will be negative, non-negative. Then you basically get a version of this. Okay, so if I have odd centered moments and I know that this state norm of deviation from the mean that is silent. And this follows from some binomial expansion and trying to do it. The intuition is so if you think of the deviations from 1, there's positive deviation from the downward negative deviation. Right? The odd centered moments being non-negative means that the negative deviations are never overwhelming the positive. So the negative deviations will be negative whenever it is give a negative contribution, but they're not kind of pushing you all the way to the negative side. So that helps you really kind of conclude that there have to be positive deviations too. Okay. So this follows from some binomial expansion and some other property. So willing to lose the norm is a simpler proof. In our case, we will slightly longer proof this side. 2k website. Okay. So why does this imply this? Okay, so why does this imply this? Let's try and do that. So assuming this time. So we're saying something about real value random variables and odd centered variables. Why does spectrum positive comes? We're going to use this to the random variable x, which is q on a random point. And on Q and a random. Let's try and use it on this side. Now its expectation is 1, and we do know that the kth norm is big. But do we have that condition? We have to check if the odd centered moments are not. Well, we can do that. Here we're going to use Fourier expansion. I can write Q of x as sum over all Fourier coefficients, you have Meka, Fourier coefficient, character evaluation on X, -1. But the -1, just take for the constant. The constant here is exactly 1, because the expectation is 1. Right? So this is just omega not equal to all the all zeros. And now you expand it out, and Fourier coefficients, of course, they are orthogonal, right? So they have to. So this just becomes expectation over. I mean, it becomes a sum over any k things. And what you get is either 1 or 0. So this is, they have to add to 0, which is may not important, but basically the thing is the sum of products of Fourier coefficient. And all of these are non-negative with respect to what k is. So this is the relevant because of spectral positivity. So technically, you could relax spectral positivity, something like this, but I don't know if you gain anything from saying that you don't need all of the coefficients to be non-negative, you just need like the sum of the Fourier coefficients to be non-negative products and so on. But it doesn't simply
Just time-wise, we started about 12 minutes late. So we'll go with 15 minutes, but we can go on until 30. Yeah, so another half an hour.
Sure, it's up to you.
We'll go on for half an hour, at least. No? No, technical question. So spectral positivity is this sort of new ingredient in this proofs which differs from the past. But has these sort of things been used elsewhere? Not necessarily the 380s.
I don't know. I mean, in some sense, I don't think so.
Okay.
So just like to relate to this, so if I take the Gaussian. So as very instead of x, I take x minus 1. So it's a mean zero random variable, all moments positive. Then this is things of the opposite of the usual Gaussian, sub-Gaussian creator property. One of the moments is large and there's another moment farther away. But it's not for the same random variable, it's 1 plus 2.
Yeah. It's 1 plus the Gaussian, yeah. Right, I mean, that's the important thing, right? Because otherwise, the norm of x minus 1 k prime is bigger than this. So you don't gain anything, but it's that 1 plus, kind of a reverse priming, I would call it. Yeah, and one thing is like, spectral positivity is not that hard to get in some, like, let's say you're trying to do something pseudo-random matrix. You want to, you have a distribution, it might not be spectral positive. I take 2 independent things, XOR them, I get spectral positive. I double my sequence. So it might not be that, rare an object.
Gaussian.
Yeah, Gaussian spectral positive for sure. And like, if I have any distribution, just take convolution 2 times. If you want a hard distribution for something, you might be happy with saying the XOR of 2 things gives me a hard distribution. That's also good enough for many applications. You're only increasing circuit size or seed length only a little bit. Question is whether this could actually be useful for some other things. That's something that we're thinking about. We're not sure. Okay. So that basically takes care of step 1. Right, the spectral positivity part is done, and I'll tell you about step 3, and then that was almost periodicity part. And this is also actually very concrete. And
prior to this, the intermediate step is now we know there's a large set on which it takes a large value. You want to get a sum.
Some set, yeah.
Step 2 would have given you a sum
some
set.
set, exactly.
Okay.
Okay. So, right. So before going here, let me talk about a little bit about step 2 and how things work. Okay. So for that, again, this normalization of densities works out very naturally. And this is something we do in paper, which is, okay, so let's say I have a function. And I'm going to define some measures. Think again of f as a density always. Right? I'm going to define some measures. The first measure is what's the best subspace that is correlated with that. I fix the codimension k and ask, okay, what's the best subspace that is correlated with that? I'll call this the subspace correlation thing, which is max for all v, codimension of v is less than or equal to k, v a subspace, and the inner product between s and the indicator function of the density of this. Okay. And again, as usual, I mean, the inner products will also be expectation inner products. Okay. All right. And under this normalization, we have to just work with the normalizations a little bit. But basically, density increment. If you think of f as a density, and I want to say when I restrict to the subspace, I increase the relative fraction a little bit more. It corresponds to saying that let's say I want to go from something like, I have constant fraction density delta to 1.01 delta. I want to increase it by a multiplicative factor. Under the right normalization, which is you have to go through some constants carefully. But it exactly corresponds to saying that there is a subspace which under this, inner product has a higher value, has value which is like 1.01.
What k?
But whatever k this is. So if this is true for some k, then you get density increment onto the subspace with codimension k. The density increment is constant factor. Okay, this is just working to the normalization, no matter of fact, it's just straightforward.
Yeah, both f and 1 we are between 0 and 1.
Sorry?
No, both f and indicator of we are between 0 and 1. Okay.
No, it's not. No, A is there. It's a density.
Density, yeah, that's why density normalization is very nice. Like everything just becomes, now you don't have to say, okay, I have to find a subspace where the number of elements is increased and so on. I just need to find a subspace where this inner product is 1.0.
So in earlier proofs, you take k equals 1, like looking at a single.
Like Roth's thing was k equals 1. Yeah, exactly.
And there the gain you get is not always, it's like delta plus.
Yeah. So you don't get, yeah, exactly. In earlier proofs, you don't, this is giving constant factor thing direct.
So to get there, you have to do it with
Roth proof would sort of say that for k equal to 1, this is 1 plus 1.
1 over
delta.
Yeah, whereas again, delta is like, basically it will go into
Delta is the
the
largest value that f2.
exactly.
Sorry, 1 over delta is a value.
Yeah. Okay, so let's, I think this makes everything, all the calculations a bit more, easier to handle. You don't have to think about, okay, did I increase my density or not? I just need to find a subspace field where the inner product is taking a bigger value. Okay.
So in like Roth's proof, instead of looking at one Fourier wave, maybe you have a whole bunch of them with the k of them that are small. Can one look at it? Is looking at the intersection of those?
That's kind of what happens in the proof. But the problem is that, you peel them up one after the other. So that's why you end up with this 1 over delta things. If you can find some of all of them in one go, you're doing much better. Okay. All right. So the other definition I'm going to use is I'm going to call f star comma k, which is the same thing but measures increment onto subsets. cannot use A. So I'm looking at all sets whose size is at least 3 to the minus k and the size of the universe. So basically missing k directions, or the entropy deficit is k. Okay. And now I'm looking at correlation with so intuitively, if I take a subspace, convolve with itself, read from the distribution of the subspace and convolve with itself, what you get? Subspace, which is exactly what this is. Right? So now we're just relaxing to say what this is the exact, this measures density increment onto some sets. Okay, by the same normalization, density increment onto some sets is equivalent to saying that this guy is 1 plus 2. Okay. And the beautiful thing is that Sanders connected these two things exactly for any function f. Okay, so we use it for f, which is itself a convolution, but it's true for any f. Okay. So I mean, it's also present in many other works, but the version that we use is due to Sanders. So I shouldn't just say Sanders. I think Truth Park, they had something, and then it kind of builds on many things, but the exact version that we use is from there. But let me not do radiation problem. Let's say almost periodicity. Okay, almost periodicity says that for any f which is bounded, it goes into the parameters, but f is bounded. This guy is at least epsilon squared. Okay. For any
This 4 is the 4 and
4, yeah, exactly. This is the last.
the Sanders 4 you have.
Yeah, exactly. Yeah, it's kind of connected to that. Yeah.
So you would get PFR if
This
this
is 4
statement 4 becomes 1.
Yeah, this PFR is pretty much equivalent.
Okay. So what's the statement for login?
That this should be true with L equals basically the order. Yeah. So this is saying that the correlation with a subset, okay, is not much worse than correlation with the subspace, but the codimension is you're losing something. And it's an additive gap. Again, F is bounded just goes into what is epsilon is. So okay. Does the statement make sense? So now it immediately implies that basically if I density increment onto a subset, maybe this is like 1 plus 0.01. I'll choose epsilon to be 0.05. Then I get basically density increment onto a subspace with codimension O of k to the 4. Okay, and then similarly 1.05 is exactly the density. Okay, so getting it to some set immediately gives you this. You don't have to do it. So this is a very clean part. If you borrow from it, existing. All right.
This is the previously good.
Previously good, yeah. And used in similar ways in many other words. I think it was used for the creative problem also in Bloom and Sisask work. Like we also use this almost periodicity, and it's a proof that they have where it slightly improves the quantitative parameters, and I think it gives us this more explicit. Not really. In fact, in the entire argument, we don't really work in the Fourier space. So we, except for the spectral positivity when we prove that lemma, but we never have to, like this proof of this uses it, but we never work with Fourier representation or anything in the actual argument. If you look at Roth's proof, the way he finds the largest coefficient is by looking at the Fourier coefficient and so on.
Right, is this there? Viola's write-up of Sanders.
I think Charles.
Sure, yeah, sure.
It's kind of there, but not, I don't think it's stated in this exact way. You don't think so?
Recall the statement from Charles.
You seem to or you don't seem to?
I don't.
Yeah. I don't think it's stated exactly this way, but that's the main implication. It's one of the things there and we can use it, and I think it's a clearer way to state something.
No, but I mean, like Charles statement, that is equivalent or it's
I
different?
think so. I mean, again, the final proof is something else, right? This is an intermediate step. This is one of the intermediate steps.
So statements occur in this sort of form. I've never seen it in terms of so cleanly written in terms of these norms. But that's also standard, you're saying.
I think, this is kind this is standard thing. I don't, okay.
So if you take a sum set, do we sort of know what its Fourier coefficient sort of look like? In the sense that I'm trying to see, is there a way in which once I know I have a sum set and I have a density, like very good density increment there, can I somehow run Roth's proof at this point to actually find a subset? The problem is I don't know what my ambient world is.
Right. I don't think it's that easy. Like we really have to use this. The way this works is like intuitively, once I find density increment on the sum set, basically you say if I take 4 copies, I get an exact subspace. That's what Sanders' result implies. And from there, you have to do some stuff to get such a clean. Right, like I said, if there is a subset, which is when you add it 3 times, you get the exact subspace. Sanders showed it for 4 things. There's a big subset A prime, so that if I take A prime plus A, 4 A prime is basically A subspace. Okay, so in the remaining maybe 5 to 10 minutes, let me say a little bit about the sifting part. Okay. So, what's that guy? We start with the assumption that epsilon has become epsilon. Okay. And what we want to conclude is that there is density increment on difference. Under this notation, we want to say that this implies that K prime roughly for words. Yeah, something like this is what we want. Okay. And it gets slightly worse. The parameters, let me not. It's going to be K log 1 over delta. K prime is not going to be exactly this. It's going to be K log 1 over delta, but let me not go into the quantitative rates yet.
But the dependent on K is linear, not like.
Yeah, dependence on K is linear. So basically, K prime will be something like K times alpha.
Epsilon.
The original delta, the density of K.
The density, okay.
So you lose like a square here. Like if you think of K, we started out with K being log 1 over delta.
Oh.
So it becomes log squared 1 over delta. You go here, it becomes log 1 over 8. And then it becomes like log 1 over 9 because log to the 8 and then log to the 9 because you have to repeat it log 1 over delta times to get a contribution.
So the delta is the density of E.
Delta is the density of A. But this is what, so we are always working with A. Yeah, we don't just use this assumption.
Yeah.
We also need that the density of A is A has density. Okay. I mean, this does imply something about how big A is, but it's not really have. Okay. So this is what we want to say, that there is density on this answer. Right? And we show something slightly better, which is so the start thing, I can define it for any density. It doesn't have to be like a set. Right? I can define it for any density. And we actually show it this. I start with the assumption that difference convolution indicates non-fixed. This implies that there is some concept is correlated with the convolution. And the point is that this implies this by some averaging. Because I know that there is some concept is correlated with two independent copies. By averaging, there should be one fixing of the second thing where that also happens. Yeah, that's kind of actually useful because this statement, as I stated, it is not necessarily true. You have to take two different things, not B plus D or B plus C. But they can apply shift here and there. Yeah. That's kind of annoying, but you can take care of this. If I'm working with the different convolution, I can only work with some subspaces. I don't have to work with affine spaces. Okay. All right. So how do we do this? The starting point is, so what does this mean? Again, the intuition is that, okay, we want to say that there is a structured set where the density is taking big values. Right? This implies by this sort of averaging thing, if I say S is, okay, look at all points C where is bigger than 1 plus epsilon. 2 I think is 0. 2A. Oh, sorry, okay. Then we essentially know that the size of S is roughly like 2 to the minus 4 K times 3 to the. Okay. So knowing that the Kth norm is big implies that there are many points where I'm actually taking reasonably big values. And so another way to think about the same thing is to use duality of norms. Okay. So the Kth norm is being big implies that there is some function f where this happens, and f has some bounded norm or something like that, right? There's some witness for this function taking high values. The indicator function of S is one such witness. If I take the indicator function of S as the F, then obviously my thing is going to be big because with exactly those points where this is big. It's 1 plus epsilon. Okay, the epsilons can change for the matter. Right. So what we really want is to say that there is a structured witness where this inner product is big. Right? So, oh, my F has changed. Let me make it that's better. So our F is going to be this. Think of this as our F in that equation. We want to say that there's a structured thing where the inner product is big. All we know is that there is some witness. In fact, we know that S is something like this. The indicator of S is one such thing. Okay? We really want to find something much more structured. Fortunately, there is another witness for this inequality, okay, which always works and which is much more useful for what we are going to do.
What you know about G tables is bounded from the dual.
Exactly, you bounded in the dual one. That's what you conclude. Okay. And so the witness that we use is, okay, so let me define it. So the witness that we use, I'm going to call Q. Is it's not specific to the difference convolution, it can work with any n. The non-negative n has some properties, but let me just take it for this time. The witness that we're going to use is the function that is for some density G with G dual norm. I mean, that's the whole one. That's a duality. But there's another witness which always works, which is take your original function, raise it to the kth power. It's kind of a moment argument, right? I want to pick out those points where my function is big. What is one way to bias my distribution to pick out those points where functions taking big values? Just raise my density to a sufficiently high power, right? Then those things will dominate much more than others. Okay, if my value is 1.5 somewhere, it's now become 1.5 to the k, whereas everything else is still 1. Okay, so that's the idea. You take the density which is proportional to the k square. Okay. So formally, Q of x is basically you have to make everything in density. So it's not specific to difference convolution, but that's what we're going to use it for. So, yeah. And some calculations show that this is always the case. If in fact, you know something stronger. The amount of mass that Q puts on set of points where my density is small is tiny.
So Q minus 1 more than
Then we have exactly the same place.
Actually, I might be fudging the k anyway. No, it's probably not the same k. Like, the case keeps changing by constant factor. Sorry, say it again.
In the expression for image, in the denominator shouldn't be scaled by the dual norm.
No, it's the k norm because I want it to be a density.
But here you are saying you should have bounded.
So this we always get. This we always get. This is a witness that is always true. But this is something that we show. Like, for any function, if I raise it to the k power, it kind of picks out those points where you're big. It's a density which biases you to those things where you're taking high values. Okay. And this is, and again, this is going to be k prime and so on. So, yeah, I'll tell you. It's almost there, almost there. Okay. So basically, it's going to the structured witness because I want to start from a G here, which is better for finding the structure.
You haven't yet used G, no?
Or whatever function I'm going to use.
Yeah.
We're not going to use this G at all. So whatever function I'm going to plug in there, right? I'm going to use some witness for the inner product being big, and then I'm going to refine the witness.
So the witness is this.
The witness is this. The first guess might be use the witness as the indicator of S. That's not very good. Okay, but if you use a witness to be this, raising to the fifth thing, that works good.
What's the equation to see that's
Yeah, the theory resistance. Okay, so at least the intuition for why it might be a weakness is,
Why didn't you give you a structure?
yeah, that is not there yet. That's where the shifting comes in. The shift and intersect that hasn't shown up so far, right? That's going to come next. Okay, so this is what we have, all right? And okay, so the real shifting lemma is the following. It's just a statement about this specific weakness. Okay, I have to define this Q. Okay, and maybe let me call it, in the paper we call it at Q. Okay, but let me use Q because it's going to be cumbersome. But the point is that Q is already something which depends on it. Okay. Let H be any function. Telling you that I have some function which has small inner product with Q. The function here is one is it can be any function. If this is true, then there exists A prime, which is a subset of A, and size of A prime is let me just take these things a little bit.
The K is built into the hypothesis because Q itself is a function of A.
Is a function of K, exactly. Okay, this is saying for any function, somehow if my K square is not correlated with it, okay, then there is an A prime within this guy, which the difference convolution is actually correlated with it.
Sorry, what is A?
A is the definition of Q,
So it's A, K, and then Q is defined based on it. And
yeah. Okay. And you can also show this with the star, but I think the star version is more useful.
okay, why is this what we want?
So let's see. Okay, so that's a good question. So why is this? I'm a little bit. This is the star. Okay. Whether the star or the circle gives to this, we'll figure out. But one of those gives, but the statement is superposed. Okay. So suppose this is true. What is it saying? It's saying that the convolution here is such that its correlation with all those points where your density is small is very small, epsilon over 5. Yeah. Suppose you found this. So now this implies that I want to say this implies
That's just answer. A prime is A prime.
yeah, A prime exactly gives me my subset. And if I apply this to 1 as bar, I know that this is at most epsilon over 5.
Yeah.
Okay. Meaning it's almost all of its mass is actually on those points where the original thing is big. Okay, which is what you wanted. Right? So this implies after some calculations, I mean not too many things, but basically Right? Only because, S is all those points where that function is big. Right? With one S is big, and that implies that you're big.
S is almost, S itself is almost close to the subset.
Or it is the opposite. There is a subset which is completely contained within S.
Yeah.
That's the implication. Which is good enough for getting the star mark, which implies that the normalizations you have to be a little bit careful, but they work out nicely.
And this is very
This is what?
this level.
This lemma is what we call sifting in paper. That basically it works as long as you start from any k, you define it this way, then you get this.
This was not intended. This kind of level.
Yeah, it's not used in this exact way.
For example, you the idea of not going through the natural witnesses,
Yeah.
but to this analytic witness.
Yeah.
Yes.
There is some precursor to it in a couple of papers. I mean, we were inspired by them. Like there's something in Gower's style where it does something similar. And how we prove it is also by this dependent rounding thing, which is present in other papers. So I'll tell you why this is true. It's exactly where the shifting thing comes in. Remember you shift the subspace and intersect that hasn't shown up so far. Right? Where does it come in?
That comes the proof of the shifting lemma.
It comes in the proof of the shifting lemma. Okay. So proof of SL. Okay. So your A prime is going to be pick S1 through Sk minus 1 uniformly from and then A prime is A prime of S. Maybe use a different thing here and then it's okay. Okay, you can define it this way. The actual L, I think, is just minus 1. Yeah, I think we can use it. Okay, so we're going to show that this works. This gives you that thing.
On average.
Why is this true? Actually, it's true almost because it's true in a very strong sense because there is some normalizations you need to do, which I don't want to do. Okay, so I'll put the equality in quotes. Or maybe let me do this. I think it's worth doing it properly. So you really need it for the stars, but let me do it for the circle. Otherwise, you have to do minus, plus, and so on. So let me just follow them. So let me define this sort of additive energy function that people use that comment. Right? It's just counting how many ways can I write x as the difference of two things from my set A. Okay. It's really just proportional to some normalized, just count instead of the density. It's proportional to this, right? And the great thing is for any edge, this is the lemma. Call that guy over there. My edge. This inner product for any edge, basically Q comma edge, okay, is equal to the expectation of so you have this exact equality, like, forget this normalization, forget all this. And what it's saying is the inner product Q comma H for any H is equal to what you get in expectation of some normalization of mu A circle mu A. The A prime basically. Right here. So maybe here, I'm defining this for any set B. I don't know. For any set B, I can define the additive energy. I'm going to look at what happens when I use this shift that's set here. Okay, what is the additive energy? This inner product Q comma H is equal to just 2 copies of A prime of S. And inner product with H, but the expectation over S. And this is an exact equality. Okay. And when I said this normalization here, the normalization constant is A prime of S squared. Right. If this expectation was not here, but like it is divided by this, then we could exactly be saying like the inner product Q comma H is expectation over S of mu A prime of S, mu A prime of S inner product with H. Not exactly true. Instead of the normalization being in the numerator, you have to do the expectation both ways. Does the statement make sense?
And this
has been known before and used before.
And this is easy to, this is just you open it out and
You just open it out and everything works out. Okay. So when you open it out, basically there are 2 copies of A here. You do the kid thing, everything like plays out nicely. It's the same distribution on both sides, like the counts are exactly the same. It's true for any H. For any H, this equality. Okay. And now you just do like a first moment method kind of thing and say, because it's true over expectation, there is some S for which this is true. So it implies that there exists a set of shifts where
So you mentioned additive energy. How does it tell you whether a set is a sum set or not? For sum set, this number is large.
no, we kind of describing the subset just by additive energy is like the distribution that you would get for the subset B plus B minus B. So we're describing the subset explicitly.
Okay.
We're describing the thing that goes into the subset. We're not describing the sum directly. Okay. And the reason is that, basically, okay, I'm going to hand wave and say this lemma by the first moment method implies that there exists some S such that okay, so imagine this expectation was not here, but this is actually here. And it's the same thing, you just have to do 2 more lines of calculations. Okay. Then you're getting this is true, which is exact. This quantity is equal to this. Okay, and to get this, you have to use the fact that the expectation of this guy is big, and then work with the constants. Like you have two things which have happened with constant probability. You make the constants like more than half, and then both of them. Okay. But all of the magic is kind of in this equality, and then it's first moment method. That's why working with this witness is very nice, because somehow it just fits in right away into this setup. Okay. Right. Let's just stop with that.
Any further questions? And the outline is similar for other Bayesian groups and stuff.
Yeah, you have all of these steps, but then you have to work with like board sets. Okay. Yeah. There's this notion of a board set, and the rank of a board set corresponds to the 4-dimension of the subspace.
Okay.
And
So there will be some sets, but instead of subspaces, you will have board sets.
Basically, instead of subspaces, you'll start looking for sets which don't grow too much under addition. The main property of subspaces is that V plus V is V. And there is a notion of board set which tells you that if it's a board set, then V plus V is not that much bigger than V.
These are like arithmetic progression.
Arithmetic progressions or something else. In over abelian groups is just kind of defined in terms of Fourier coefficients, more or less.
Yes. Thank you.